Hello everyone, this is Mike Dowding with the SD Minds Physics Department, and we're continuing our discussions on Chapter 7 material. Today we're going to actually finish up the chapter by looking at some more examples with work and also define a new term called power. So what I'm going to do first of all is go ahead and define power. Otherwise I usually forget and I have to go back and redo this. But our definition of power is going to be the rate of transfer or transformation of energy. But we can actually narrow that down with another definition. Whenever we transfer energy, remember that requires a change in energy from one object to another, or a change in energy of one type of energy to another. For instance, we have kinetic energy. We can take that energy and we can convert it to other forms of energy, like thermal energy. Through heat transfer, we can we can transform it into potential energy, which we're going to learn about in Chapter 8. But everything that I just highlighted there is basically just the definition of work. And we said that work is a change in energy. And that energy is going to change through either being transferred or transformed into another type. Then we have this part right here, which says rate. And rate, well, that refers to how things are changing, but with respect to some other variable. And in our case, that rate is going to be a change in energy with respect to time. You can have other types of rates. For instance, you can have a change in position with respect to time. You can have a change in velocity with respect to time. Those are both rates that are dependent on time. But you could also have, say, a change in velocity with respect to displacement. So as you're traveling down the road in your car, you're speeding up, that velocity can change with respect to your position, in addition to changing with respect to time. So typically whenever we hear the term rate, it's usually a time dependency, but that doesn't mean that it has to be. It could be something else. And so since we've taken our definition of work, which is a change in energy, and we divided that by time, well, that becomes our definition of power. So power is work over time. And what I want to do now is go back and revisit how we evaluated work that was done by a particular force. And we had two ways of doing this. The first way, which is my preferred method, is we take the magnitude of each vector along with the angle theta that exists between those two vectors, and the cosine relationship applied to the magnitudes of each of those will then tell us how much work is done by that force. The other method that we have for evaluating work was if our force and displacement vector were presented in component forms. So you might remember this from a previous video. If I have a three-dimensional force that has x, y, and z components, and I have a three-dimensional displacement with x, y, and z components, then those components can be combined using a similar approach to the cosine, and it resulted in an expression that looked like this. And this would give us the same result as the top method would. So which equation you use, really that depends on how the information was presented to you. If the information was given to you, if you already knew the magnitudes and the angle relationship, go ahead and use the top equation. But if all you know are the components of your vectors, then it's more beneficial to use that bottom equation. Well, since we have those two methods of evaluating work, what we need to do next is apply our definition of power. Because power says we do a certain amount of work in a certain amount of time. So power equals work over time. And first rule of algebra, what we do to one side, we have to do to the other. And at this point, I would like to combine the time with one of the terms up in the numerator. And our choices are force, displacement, or that cosine relationship. But I'm going to go ahead and combine these two, because we already know that displacement over time is equal to velocity. And so this statement can be rewritten as force times velocity times cosine of theta. I guess the real question now is, can we go backwards in the dot product relationship and write power like this? Can I write power as the dot product of a force vector and a velocity vector? And the answer is absolutely, because up here in this equation, we already know that velocity is a vector, and our equal sign there now not only means that I have to have the same numerical value on each side, but I have to maintain the same vector direction on each side. And so that displacement, since it started off as a vector, well, we can divide a vector by a scalar and still get a vector, and that's exactly what we get with velocity. And so this is a valid means of expressing the power for an object. So how do we use that? Well, if I have a mass and I apply a force to it, that mass will start displacing, but Newton's second law says F equals ma. And so my mass is actually going to be accelerating. Is that acceleration zero? Is it non-zero? Does it matter? Well, turns out it doesn't matter. What matters is how fast we're going at any given moment in time. And so this velocity has to be an instantaneous value. it's very possible that we can be accelerating as we travel this displacement, but that means, constantly changing velocity values along the way. If I want to know the power at any given point, then I need to select the velocity at that given position. And so I'm going to say that this is instantaneous velocity, velocity. This needs to be an instantaneous velocity. Okay, well, let's dispense with all of this extra stuff here. And let's say that we have a force of 100 newtons. And it starts moving our mass to the right. As we start moving, that force accelerates the mass. As we accelerate, the velocity changes. And so at some point in our movement of that mass, there is an instantaneous velocity that has a value of 5 meters per second. So, what is the power at that instant in time? Well, I've got my force vector on the diagram. So I know that I'm moving to the right, and it makes perfect sense that as we accelerate to the right, any velocity vector that we work with is also going to be to the right. And that means when we evaluate our dot product for the force vector and the velocity vector, well, I have 100, I have 5, and I have cosine of 0 degrees because these two vectors are running parallel to each other. And that means I have a power of 500. And now is as good a time as any to talk about the units for power. Well, the units, they're right up here. We have force, which is in newtons. We have velocity, which is meters per second. Or, as we already know from our discussions with work, a Newton meter is a joule. So we have power in the amount of 500 joules per second. So we are transferring 500 joules to this object every second by applying the force to that mass. But there's another unit that we can use. A joule per second is what we call a watt. And that's how we're going to measure, our power is in watts. And this will actually be one of the few units that I write out the full name, because I don't just want to write W, because then, this soon after working with work, somebody's going to mistake that. So you'll always see me write out watts. Okay, that's how we use this method, this method of evaluating power. So how would we apply this method to evaluating power? Pretty much the same way. We're going to start on the left and divide our work by time, which gives us power. But first rule of algebra says what you do to one side, you have to do to the other. And don't be misled. This time value is applied to all three of the terms in the numerator. So everything in that numerator has to be divided by time. Once again, we are faced with the decision, what do we actually divide the time with? Is it going to be the force or the displacement? And I'm just going to keep with the theme here. I'm going to divide my displacement components by the time. What this is going to produce is components of the velocity vector. Because what we have on that first term is the x component of displacement divided by time. And so really this is just telling me how fast I'm traveling along the x direction, and we would just call that velocity in the x direction. As for the other terms, well, we're doing exactly the same thing. I have a y component of displacement divided by time, so that's going to turn into a y component of velocity. And then the z component of our displacement will turn into the z component of our velocity vector. And we're done. From here, I would need to know components. We'll say 2, 3, 4, I, j, k. So there are the components for the force that I'm going to use. And then, just like the other expression, we need to use an instantaneous velocity. That's not a problem, because I can have a vector with multiple components, and I can put all those components back together and get magnitude and everything else that I need. And so yes, this is an instantaneous velocity. All these values are instantaneous values in the respective I, j, k directions. And now we put everything together. In the first term, we have fx times vx, which is 2 times 1, which is 2. Then we have fy times vy. 3 times 5 is 15. Fz times vz. 4 times 7, 28. And all of that is power. Remember that our dot product, regardless of how we're evaluating it, whether it's the magnitude and angle approach or the component approach, results in a scalar. Okay, power is work over time. Work is a change in energy. Energy is a scalar, so work is a scalar. Time is a scalar, so power is a scalar. Now, we got to add everything up. We got 28 and 2 is 30, plus 15 is 45. 45 what? 45 watts. So whatever this force is being applied to, whatever mass, it is transferring 45 joules every second. That is what this is telling us. Okay, well, I have one more example of the definition of work that I want to show you. And that has to do with variable forces. Okay. This is something brand new, because up until now, everything that we have done has pretty much insisted on the fact that any accelerations we work with are constant. The only exception to that is if we had some kind of position function that had a very high order time dependence within it. If I were to take a function like this and take two derivatives so that I could get a acceleration function. Let's see, our first derivative would be 12t cubed plus 16t, and then our next derivative would be 36t squared plus 16. So you can see here the function for the acceleration is variable. And so our kinematics equations that we derived, in order for the math to work, we had to use a constant acceleration. Now we're going to consider cases where the acceleration is not necessarily constant. And to do that, we need a force that is not constant. So in other words, we need a force that is changing as a function of something. There are plenty of variables that we can choose. We could have a time-dependent force. We could have a force that changes with respect to position. We could have a force that changes with respect to velocity. There's lots of options out there. But we're going to go with a case scenario that is pretty common, and that has to do with springs. So I'm sure everybody has probably played with a spring at some point, maybe a slinky, or maybe you've deconstructed your pen and you found that little spring in there and then you lost it and then your pen doesn't work right anymore. But we're going to draw a spring on the screen, and I'm going to anchor one end of the spring to a wall, and then I'll leave the spring alone for a little bit, because after we play with the spring, it might still be bouncing around a little bit. So I want that spring to come to rest, and I'm going to measure the position that the spring comes to rest, and I'll label that 0, and we're going to call this equilibrium. This is the equilibrium position of that spring. And one way to think of it is, springs are very much like college students. If you try to remove them from rest, they're going to fight you. So if I try to apply a force to this spring, and I'm going to put a little plate on the end of the spring here, so later if I need to, I can maybe attach a mass to it. But if I apply a force to this spring and I start stretching it out, that force is going to fight me. That force is going to produce a counter force, which falls in line with the third law, Newton's third law. So for every force, there's an equal and opposite counterforce. And what we find out is that the further away from the equilibrium position that we get, the stronger and stronger this force becomes. So our spring force is a variable force, and it varies based on how far away we are. So it's going to vary based on position. What we need to do is find out, is there some kind of equation that we can produce that describes that force? It's also worth noting that if I were to compress the spring, so instead of stretching the spring out, if I compressed the spring, we would see a similar situation. If I compress the spring back, the spring would produce a counterforce. And now that we can see these two pictures, it's worth noting that the spring force always points towards the equilibrium position. So spring force always points toward the equilibrium position. So, just like a college student, no matter which way we try to drag you out of bed, you want to try to get back to that equilibrium position. And the more we drag you away from bed, the more you're going to fight us to get back to bed, because that's where you're at rest. That's where you like to be. All right. Well, if we take one of these situations, and it doesn't really matter if it's the stretching or the compressing scenario, but I'll go ahead and use the stretching scenario. So we'll have our spring at equilibrium and then stretch it out to some distance x. And so to do that, we have to apply a force to remove the spring from its equilibrium position. And while we are doing that, the spring is providing its counterforce. And these two forces have to be equal in magnitude to each other if the third law is in fact going to be valid, and it is. So let's graph what would happen in a real situation. Let's take the amount of applied force and graph it versus the spring force. Well, if the spring force always has to have the same value as the applied force, what happens if I increase the applied force? Well, then the spring force has to increase. And so we would see a perfectly linear one-to-one relationship between those two. But we can see that there's also the dependency on position. And so we'll try another graph. For this graph, we'll measure changing position and change in spring force. And in this case, what we see is actually another linear graph, but it's not necessarily going to be a one-to-one graph. And at this point, I want to remind you that not every spring is the same. Some springs are very flimsy, some springs are very stiff, and so these spring force versus position graphs can look quite different for different springs. So I'll just go ahead and put in a few different colors here. So every one of these graphs represents a different spring with a different stiffness or a different rigidity, if that's even a word. But the slope of each one of these lines, slope from the algebraic definition is rise over run, but rise is the value of force, run is the value of x, and so what we have is the ratio of the spring force to the position value. And we're going to call this ratio little k. And little k is our spring constant. So little k measures just how stiff or flimsy that particular spring is. So right here with the first line, which is very steep, in this case we would have a pretty high spring constant value. This would be a very stiff spring because we're getting a very large amount of spring force out of a very small displacement. And then as we move down the examples through the other springs here, down here we would have a very small spring force because we're getting a very small force value out of a very large displacement value. And well, this actually tells us what the equation for our spring force needs to be, because we have a ratio of spring force to position which is equal to k, but once we've measured our k value, that's not going to change unless we do something to the spring to damage it physically. But that spring constant, as the definition implies, should remain constant. What changes is that position value. And so all I've done is I've moved that over to the other side. And now we have a means of measuring the magnitude of our spring force at any position value. Okay, well, let's see how that works out. I'm going to put my spring back at equilibrium, and that's the first thing I'll evaluate. What is the spring force when the spring is at equilibrium? Well, in that case, x is equal to 0, and so there shouldn't be any spring force. And that's because the spring is already at rest. The spring doesn't need to return to equilibrium because it's already there. If I remove the spring from equilibrium, so we'll go ahead and stretch it out here, I move out to some positive value, we'll just call it positive x again. But our spring force needs to point back to the equilibrium position. And we are technically dealing with forces and displacements, and so I'm going to put in a reference frame here. To the right is going to be positive. And once I do that, there's a little problem that pops up with our equation here. Because k is a constant, if I move from the equilibrium position out to the point positive x, well, that gives me the magnitude of my force, but the force is pointing in the opposite direction. My force, well, it doesn't have a negative sign there. And I can't have a negative spring constant. That wouldn't physically be possible. So everything over here says I have a positive outcome, yet my spring force should be pointing in the opposite direction. If I try the opposite scenario, if I compress the spring back to a position of negative x, my spring force is going to oppose that by pointing back towards the equilibrium. And we run into the same situation. I have a spring constant of k. My displacement is now negative x, yet the spring force should be pointing in the positive direction. So in each case, we're getting essentially the wrong outcome. I should have a negative sign on this force, and I should have a positive sign on this force. And so what do? Well, we'll take the equation that we had for the magnitude of our spring force, and we'll just fudge that negative sign there. Because it doesn't matter which case we're talking about, in any direction that I try to remove the spring from equilibrium, the spring is going to oppose us. So whether I move in the positive direction or the negative direction, the spring always opposes us. And so I need my spring force to have a sign notation that is opposite of the value that is inserted for my displacement. Right, so that's our spring force. Now we have our spring force defined. It is negative kx. Well, I've got a spring force, and it's variable, and that's what we wanted for this next discussion, because we said that we were going to talk about variable forces in this next section. So let's attach a mass to our spring. So I'll attach a mass of m to our spring. We'll go ahead and put that spring at equilibrium. And the next thing I want to know is how much work will a spring force do? Because we've been moving this spring back and forth, and every time we move there's a displacement, and as we move back and forth there is a spring force that's going to point either in the positive or negative direction depending on what we're doing. And so what kind of work is that spring force going to do? So again, we will take this a step at a time. We're going to start with stretching the spring out to the position positive x. And so as we displace our spring, the spring is going to fight us. The spring wants to go back to equilibrium. And our first attempt at this might be to try and use the first form of evaluating work done by a force. So work is F dot D. We have a spring force. We have a displacement, which is X. And then there's a cosine relationship between these two vectors, but those vectors are pointing in opposite directions. That makes 180 degrees. Cosine of 180 is -1. So we get a minus sign. But then we got to be careful because right here, these symbols are saying we need to use the magnitude of these vectors. Okay, well the magnitude of my displacement, that's no problem. It's just x. But our spring force was negative kx. Okay, so I'll put a negative kx in there, but what is the magnitude of our spring force as we're displacing? This value of x is the value of our displacement. That's a fixed value. But this value of x, that value is constantly changing as we move away from equilibrium. As we get further and further away, the magnitude of our spring force changes. So the question I pose to you is, what is the magnitude of a variable? And if that sounds like a weird question, good, because it really doesn't make sense. How do you get the magnitude of something that's constantly changing? And you don't. So what we need to do is we need to figure out, as our force changes, our force magnitude is going to get stronger and stronger and stronger as we displace. Can we break this up into little segments? So can I find out how much work the force does during this first miniature segment? And then after the force changes its magnitude, can I figure out how much work it does during this next segment? And the next segment, and so on and so forth until I've added everything up. So this is where our calculus is going to take over. And I'm going to go ahead and stop the video here because I've already covered quite a bit. I'd like you to take a break. I'd also like to take a break. And when we come back, we will derive work done by springs. We've got the force for a spring, so now we need to figure out how much work that spring is going to do. All right. See you at the next video.